Hello and welcome to Stories of Science. Here, we look back on humanity's long journey to understand the world. The questions, the failures, and the breakthroughs that slowly changed how we see the universe and ourselves. We tell science as stories. The solar system isn't ending where you think. It's still moving in the dark. Those bright comets you sometimes see streaking across the night sky, they look like random visitors, one-time guests, maybe even cosmic tourists, but stretch time out a little. Thousands of years, sometimes millions, and the story starts to feel very different. These aren't just passing by. It's more like something keeps tossing them back into the neighborhood, over and over again. Take something like Halley's Comet. It's predictable, almost polite. It shows up every 76 years like clockwork. But most comets don't behave like that at all. Long-period comets can take thousands, even millions of years to return if they return at all, and here's the strange part, they don't come from one direction. No pattern, no comet highway. One appears from the north, the next, from the south. Completely random. It's like the solar system is being peppered from every angle. And that raises a simple question: where is all this coming from? Back in 1932, astronomer Ernst Öpik suggested something bold. Maybe, just maybe, there's a distant reservoir of comets far beyond the known planets. At the time, it sounded like a long shot. A nice idea, but unproven. Then in 1950, Jan Oort decided to treat it less like a guess and more like a puzzle. Instead of waiting for better telescopes, he did something very unglamorous. He crunched the numbers. He studied the orbits of known long-period comets. Carefully, systematically, and what he found didn't sit right. Their farthest orbital points weren't random at all. They clustered in a huge, distant region tens of thousands of astronomical units away. That shouldn't happen by chance. It suggested something uncomfortable but powerful. These comets weren't just drifting in from nowhere, they were coming from a shared storage zone, a place no one had ever seen. No image, no direct detection, not even a hint of light. So Oort proposed something radical: a massive spherical cloud of icy objects surrounding the solar system. That idea became what we now call the Oort Cloud. And it immediately felt weird, because we already knew about structures like the Kuiper Belt, flat, disc-like, like a spinning vinyl record. But Oort's idea wasn't a disc. It was a sphere, a giant cosmic shell wrapping around the sun from every direction. Almost like the solar system wasn't sitting in empty space, but inside a gigantic snow globe. And here's the twist: this wasn't imagination. It was forced by the data. If you removed that spherical structure, the comet orbits simply didn't make sense. In science, that's a rare moment. Usually you see something and explain it. Here, it was flipped. First you prove something must exist, then you go looking for it. So what is this thing? If the Oort cloud exists, it starts roughly a few thousand out, already far beyond Pluto, far beyond anything we've directly explored. And it may stretch out to 100,000 or more. Some estimates even push it close to a light year. At that point, you're basically at interstellar space. So the solar system doesn't really end at Neptune. That's just the suburbs. The real boundary? Way, way out in the dark. And it gets stranger. This isn't a solid wall. It's a spherical swarm, possibly trillions of icy bodies, each just a few kilometers wide. Dark, frozen, invisible, more like cosmic gravel than planets. Most of the time, they just sit there. But not forever. A passing star. A shift in galactic gravity. A small nudge from the Milky Way itself. That's enough. And once disturbed, some of them begin a slow fall inward, heading toward the sun. That's when we see them. A glowing tail suddenly appears in the sky, not because something was created, but because something ancient just got shaken awake. Like the saying goes, still waters run deep. In space, still ice can suddenly become a blazing streak. But now comes the bigger question. How did all that material get so far away in the first place? This is where things get even more chaotic. Early in the solar system's life, nothing was calm or organized. It was closer to a cosmic pinball machine than a stable system. Ice-rich bodies were constantly thrown around by forming planets. And Jupiter? It acted like a gravitational slingshot on steroids. Anything too close got flung fast. Some objects were ejected completely, the others were tossed into extreme, elongated orbits. Over time, these scattered survivors didn't just disappear. They got stretched out, randomized, smeared into a spherical distribution. Galactic tides nudged them. Passing stars jostled them orbit after orbit. Direction lost all meaning. Until eventually, a cloud formed. Not a structure built neatly, but a cosmic aftermath of violent rearrangement. A long-term storage zone made from everything the early solar system couldn't keep. Most people get one thing about the solar system completely wrong. They think it ends at Neptune. It's easy to see why. Textbooks draw it like a neat little disk, sun in the middle, planets in clean, spaced-out rings, and then Neptune shows up like a final fence. As if the teacher just finished the last line and said, "All right, that's the universe. Done." But space doesn't care about school diagrams. That edge is actually just the bright center of something much larger. The solar system doesn't have a hard boundary, not a wall, not even a line. It's more like a fading influence that slowly thins out into darkness. Start with the planets. That's the core, the crowded downtown. Then you move outward into the Kuiper Belt, roughly 30 to 50 astronomical units away. Pluto lives there, along with thousands of frozen leftovers from planetary formation. But if you think that's the edge, it's like standing in Tokyo Station and saying, "Yep, this is the end of Japan." Keep going. Far beyond that, something even stranger begins to appear. Around 2000 out, the solar system quietly transitions into a new structure. This is where the inner region of the Oort Cloud is thought to begin. And here's the key idea: it's not a border, it's a gradient. Like fog that slowly gets thinner, but never really disappears. Some models stretch it to 100,000, others push it closer to half a light year, even up to a full light year in extreme estimates. At that point, you're basically brushing against interstellar space. So the solar system isn't a box, it's a gravitational bubble. And everything you normally picture, the sun, planets, asteroids, is just the bright, dense core. Now here's where things get really weird. The Kuiper Belt is flat, like a spinning vinyl record, everything aligned in one plane. But the Oort Cloud? It breaks that pattern completely. It's spherical. That means comets don't come from above or below. They come from everywhere. It's as if you're standing at the center of a gigantic holosphere, and that sphere stretches out far beyond imagination. Let's shrink it down for a second. If the solar system were a city, the planets would be downtown, the Kuiper Belt would be the suburbs. The Oort Cloud? That's not even suburbs anymore. That's the endless empty countryside where GPS starts giving up and saying good luck. And it might be packed with trillions of icy objects. Not planets. Not moons, just frozen debris kilometers wide, dark, and invisible. We don't see them directly. We infer them from something else, comets. Every long-period comet you've ever heard of is basically a visitor kicked out of that distant reservoir. A reminder of something huge we can't actually see. But how did all that material get there in the first place? To answer that, you have to rewind to the early solar system. And it wasn't peaceful. Forget the orderly orbits you see today. Around 4.5 billion years ago, it was closer to a chaotic pinball machine than a stable system. Countless icy bodies were colliding, merging, getting flung around. And then there was Jupiter. Massive. Loud, in gravitational terms. Unforgiving. Anything that got too close had three possible endings: get eaten, get destroyed, or get launched. Some of those objects were flung completely out of the planetary region, but not fully gone. If they didn't reach escape speed, the sun still held onto them barely. Their orbits stretched out into absurd, elongated paths, like drawing a circle so wide it almost becomes a straight line. Then the rest of the galaxy joined in. Nearby stars passed by occasionally. The Milky Way itself applied a slow gravitational tug. Over millions of years, those stretched orbits got scrambled, tilted, randomized, mixed in every direction. And slowly, something surprising emerged. A spherical distribution of leftover icy objects. Not designed, not built, just evolved through endless gravitational chaos. Like the saying goes, throw enough chaos into the system, and patterns eventually find their own shape. And this process didn't stop. Even today, it continues quietly in the background. Most of the time, those distant objects just sit there in the dark. But occasionally, one gets nudged and starts falling inward. That's when we see it. A comet suddenly lights up the sky not because it was created, but because something ancient was disturbed. And that brings everything full circle. What looks like a simple streak of light is actually a frozen survivor of billions of years of orbital reshaping. And here's the uncomfortable part. We haven't actually seen most of this structure. Not because it's hidden behind something, but because it's so far away, there's almost no sunlight left to reflect back to us. So in a very real sense, what we call the solar system is just the brightest inner region of something vastly larger. And its true boundary? Still out there, quietly expanding into darkness. You might think once you've described the Oort cloud as a giant spherical shell, the story is basically finished. But astronomy has a habit of doing one thing over and over again. The moment you think it's simple, it stops being simple. In 1981, astronomer Jack G. Hills pushed the idea further, and honestly, he made everything more complicated in a very what kind of way? He suggested the Oort cloud might not be a single shell at all. Instead, it could be layered. A structure made of regions, not one uniform sphere. So suddenly, what looked like a clean cosmic boundary starts to feel more like a subway map in a huge city. Inner lines, outer lines, hidden connections you didn't notice at first. Scientists started separating it into two parts, the outer region and a proposed inner region. The outer part is what early comet statistics pointed to: vast, diffuse, extremely spread out. But here's where things get interesting. Some long-period comets don't behave like they came from that far out. Their orbital energy doesn't quite match the idea of a gentle nudge from the outer edge. It's like they were disturbed from somewhere more compact, more organized. So Hills proposed a second structure, the inner Oort cloud, often called the Hills cloud. Much closer in, relatively speaking, anywhere from a few hundred to maybe 10,000 astronomical units. Still incredibly far. But compared to the outer region, it's almost packed. Think of it like this: the outer cloud is thin fog, the inner cloud is a buried warehouse. And that changes everything. Because if that inner region exists, then an uncomfortable idea follows. We may have been interpreting the ending of comet journeys without seeing their starting point. It's like trying to understand an entire delivery network by only looking at confirmation text saying package delivered. You're only seeing the final step. Where did it actually come from? That part is still missing. And different comets don't behave the same way either. Some have stable, predictable orbits suggesting a distant origin, others are more easily disturbed, hinting they may come from much closer in. So the Oort cloud might not be uniform at all. More like layers of different densities, each feeding different types of comets. Which leads to an awkward truth: the comets we observe are not a clean sample. They're a filtered sample. We only see the tiny fraction that gets kicked into the inner solar system. Everything else, the vast majority, never shows up in our data at all. As the saying goes, you only see the fish that jumps into the net, not the ocean behind it. So we may be building our entire model from survivors, not the full population. And that raises a sharper question. Is the Oort cloud a real, structured object, or are we just seeing slices of a much smoother gradient? Modern simulations still don't fully agree. Some produce clear layering. Others show gradual density shifts instead. But they all share one limitation: the data window is extremely small. And then comes the even harsher problem. Why can't we just see it directly? At first glance, that sounds like a technology issue, but it isn't. It's physics. Distance is the first barrier. Even the inner edge is likely thousands of astronomical units away. The outer edge may stretch to tens of thousands or more. At that scale, sunlight is barely a whisper. Any reflection from icy objects becomes unimaginably faint. A single rock might reflect light toward us, but so weakly it gets lost instantly in the background. And that's the second problem: it isn't a single object. It's a scattered population. No dense cluster. No bright core. No obvious shape. So you're not searching for something you can point at. You're trying to detect a statistical pattern in near total darkness. And the sky is already noisy. The Milky Way itself is full of light sources, dust, distant stars, background galaxies. Everything interferes. So the situation becomes strange. It's not that we can't see it clearly. It's that there's nothing clean to lock onto in the first place. That's why the Oort cloud has never been directly imaged. We only infer it through long-period comets, tiny visitors that briefly enter the inner solar system, which creates a weird scientific paradox. It shapes everything we observe, yet it cannot be observed itself. Like trying to reconstruct an entire forest just from insects that occasionally fly into your house. You know something is out there, you just can't see the structure behind it. Even modern surveys like LSST will improve what we detect, but mostly in the same way, more inbound objects, not the cloud itself. So we end up in an unusual position. We build better and better instruments to study something we can never physically reach. And at some point, the question stops being just technical. It becomes philosophical. The Oort cloud isn't hidden in the usual sense. It isn't waiting to be revealed. It's simply beyond the regime where direct observation works. It's darker than dark, not because it lacks light entirely, but because the light never gets a chance to return in a usable way. And that leads to a strange rule of modern astronomy. Not visible does not mean not there. In fact, here it becomes even stronger than that. Not visible, but required. Because without it, the entire pattern of long-period comets stops making sense. If you think the solar system is a quiet, stable place, you're missing something important. It's not still. Not even close. It's constantly being nudged. Gently. Invisibly. Over and over again. And the strange part is, you never feel it happening. Once the idea of the Oort cloud became more solid, astronomers ran into an uncomfortable realization that huge outer region isn't frozen in place. It moves. It evolves. It reacts. And its connection to Earth, while indirect, is more sensitive than you'd expect. Inside the Oort cloud, most icy bodies are basically asleep. Their orbits are so vast that a single trip around the Sun can take hundreds of thousands, even millions of years. Under normal conditions, they stay out there forever. But the system doesn't exist in isolation. What wakes things up is outside influence. The most important trigger is something surprisingly ordinary on a galactic scale, a passing star. It sounds like science fiction, but in the Milky Way, it's routine. The Sun is orbiting the galaxy at about 220 kilometers per second, and along the way, other stars constantly drift closer and farther. Most of the time, nothing dramatic happens. The distances are too large, but stretch the timeline to millions of years, and close encounters become inevitable. Astronomers have even identified future candidates. For example, Gliese 710 is expected to pass relatively near the outer solar system in about 1.3 million years. Even though near here still means far by human standards, gravitationally it's enough. Because the Oort cloud isn't stable in the usual sense. It's more like a collection of objects balancing on the edge of influence, barely held by the Sun's gravity. So even a tiny external pull can matter. And that's the key point. A passing star doesn't need to hit anything directly. It just needs to tug slightly. That small nudge is enough to shift orbits. Some icy bodies begin to drift inward. Slowly, quietly, over enormous timescales. Sometimes hundreds of thousands of years pass before anything noticeable happens. From Earth's perspective, nothing changes. But out there, a comet has already been activated. So can we predict it? Not really. Because this is a classic chaotic system. Small differences in initial conditions explode into completely different outcomes. A star passes a little closer or a little farther, everything changes. One encounter might barely disturb anything, another might redirect dozens of objects at once. But we can't track which specific body gets affected. We can't even always confirm whether a trigger event happened in a meaningful way. All we see is the result, long after the fact. A comet suddenly enters the inner solar system. It looks immediate, sudden, almost random. But the cause may have started hundreds of thousands of years earlier. That leads to a frustrating truth. We can calculate orbits, but we can't reliably reconstruct triggers. So long-period comets sit in a strange category. They look random, but not fully random. More like the occasional spillover from a system that has been slowly stirred for billions of years. Simulations try to recreate this process. They can show what might happen, but not exactly when, and not exactly which object. And as you extend time further and further out, uncertainty multiplies. A comet might arrive in 300,000 years, or 700,000. We can't pin it down precisely. We often don't know which stellar pass caused it, and sometimes it isn't even one cause. It can be a combination: galactic tides, passing stars, local gravitational shifts, a small push here, another there, until eventually, something tips, and an icy object begins a long fall inward. From Earth, we only ever see the final moment, the bright tail crossing the sky. Everything before that is invisible history. So what does that imply? If triggers depend on rare events spread across enormous timescales, prediction starts to break down. We move from "will it happen" to statistically, "it might." And the uncertainty stretches so far that it can exceed entire human civilizations. In other words, this isn't a system you can warn in advance. It's more like a slow, cosmic random trigger network running in the background. And you never know where the next activation will come from. Zoom out even further, and a bigger picture appears. The solar system isn't sealed off. It exchanges material with its environment, quietly, slowly, but constantly. Comets are the clearest example. They carry material inward from distant regions, and in some cases, they may even carry material outward over time. At the boundary of all this sits the Oort Cloud, not fully inside the solar system, not fully part of interstellar space, a transition zone, a buffer layer. Material can drift inward. It can also be stripped away outward. So the solar system starts to look less like a closed object, and more like an open system floating in a larger environment, always interacting, always exchanging, even if only slightly. And at the outermost edge, the Oort cloud behaves like a thin, fading membrane, part boundary, part gateway. But here's the important twist. That boundary isn't sharp. It's not a line you can draw. It's a gradual transition that stretches outward until definition disappears. So when you step back and look at the whole picture, the conclusion is surprisingly counterintuitive. We think of the solar system as stable and self-contained, but in reality, it's a long-lived, constantly disturbed system, quiet only because its timescales are so vast. And where we are right now, just one relatively calm neighborhood inside something far larger and far more active than it looks. The people who change the world usually just think one step deeper. If this story made you see things differently, hit like, subscribe, and save it. See you in the next story.